So good morning, everybody. I hope you all have been having a good week so far. As you'll notice, I'm at home. I had a positive COVID case in my classroom, so myself and my classroom, a lot of my students all are on the 14-day quarantine at home. So, you know, there's that. So yeah. That's why I'm at home. I do not have my normal setup. This camera on my computer is horrible because I usually have an actual nicer camera that I use that actually doesn't make me look really pale. So, you know, do what we got to do. But yeah, so that's why I'm at home. So good times. But yeah, luckily, you know, things are all relatively okay. I don't believe I haven't heard of any other positive cases. So I don't think any of my students who had contact with that person have gotten it. I got myself tested and I don't have it, so that's all good. But it has made this week a little interesting, to say the least. Yeah. So we're going to get started. Today we're going to do kind of like a chapter 10 wrap up. I've got some notes for us on chapter 10, just kind of looking at the main things throughout the last two sections of chapter 10 that we've been using, dealing with forgetting words now, like confidence intervals, significance tests, sampling distributions, and some special cases that we need to think about and consider when we're dealing with two populations or two groups, as opposed to when we just have a single population that we're sampling from or a single group that we're dealing with. So we're going to do a little bit of review. We'll have some examples, and that'll be it for today. Then tomorrow we're going to be doing some preparations for the AP exam, going through some of the steps that you should be taking to make sure that you are properly prepared as we head towards testing season. Some of you may have already gone through some of the steps that we'll talk about tomorrow in other AP classes if you're taking other AP classes, and some of you may not have yet. So this should be a fun experience for everybody. So with that, what's going on here? My Teams is laggy. That's weird. All right, so we're gonna start here. Sorry, it's different. I only have one screen, so I'm used to having more. All right, so hopefully now everyone can see my shared screen. This is our chapter 10 wrap up for you guys here. If you would like to take notes on this, I encourage that. These notes that I have right here will be posted into Canvas on the calendar and in the chapter 10 module. So you will have access to them after the lesson today, if that's something you'd like. All right, so we'll start with our sampling distribution when comparing two proportions. Since we're doing some inference-y type stuff here, we always need to check conditions. When doing a sampling distribution, there's only two conditions to check. We have to check the large counts condition and the 10% condition. Remember, the large counts condition is making sure that we have at least 10 successes and 10 failures in each sample. So that goes for both of the samples that we're dealing with. They both need to meet that condition. Also, the 10% condition is saying that our sample is no more than 10% of the population we're sampling from for both samples in both populations. If those conditions are met, we can calculate the mean and standard deviation and use normal approximations and normal calculations and table A and things like that to estimate probabilities and things of that nature. The mean of the difference of two sample proportions is equal to the difference of the population proportions. Right? And that's how we get our mean. We can calculate the standard deviation of the difference of our sample proportions with this crazy looking square root thing here. The square root of P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2, where P1 and P2 are the population proportions from each of the two populations we sampled from. Right? When doing a sampling distribution, we will typically know the population parameter, right? The population proportion, so we can use it. Once we have the mean and standard deviation, we can then calculate probabilities of getting a proportion greater than a certain amount or less than a certain amount by standardizing that value and then using table A and so on, as we have in previous chapters. And that's what we can do with sampling distributions. Then we move on to our confidence intervals. Again, we must check conditions first. In dealing with confidence intervals and significance tests, remember we should always be using our 4-step process. Checking conditions is part of the planning step, the second step in that process. Right? Our conditions will be the random condition. Either we did a simple random sample or some sort of random sampling from our population, or we have randomly assigned treatments to different groups or different populations. Right? Our 10% condition only applies when we're sampling without replacement. So if we're conducting an experiment, but we are not sampling, right? We haven't randomly selected the people participating in the experiment. They were just the people available, or the people who volunteered, but we still have random assignment and we're meeting large counts. 10% condition does not need to be checked. Right? If you check the 10% condition when it is not necessary, right? So when conducting an experiment, essentially, you could lose credit on the AP exam. Okay, so just be careful of that. You can say, hey, normally we would check 10% condition, but in this case it is not necessary. That demonstrates that you understand when you should and when you should not use the 10% condition. That's a good thing to do, right? Lastly, we have large counts, which is the same as we said previously. Once conditions are met, we use a 2-sample Z interval for P1 minus P2 for our inference method. Okay, and that's this crazy formula here, the difference of the 2 sample proportions, P hat 1 minus P hat 2, plus or minus the critical value Z star. And again, this critical value is found based on the percent confidence interval that we're looking at, using that and table A. So kind of like work backwards into a Z value or Z score. That becomes our Z star as a positive value. Right, so for example, if we had a 95% confidence interval we were interested in, that leaves 5% for each of the 2 tails split evenly. That means 2.5% of that is in each tail, meaning we look for 0.025 within table A. 0.025 will go along with a negative Z value when we go back out to the left-hand column and the top row. We would then use the positive version of that as Z star. That is our critical value. And we multiply that by the standard error, which is everything in the parentheses here. It is essentially the same formula we just saw for standard deviation, but the standard error is the standard deviation based on our samples. Right, so we're using P hat 1 and P hat 2 in place of the population parameters that we used for the standard deviation in the sampling distribution. Other than that, it's the same calculation. All right. Then we have significance tests. All right. Again, we must check our conditions, random, 10%, and large counts. Once again, 10% condition only applies when sampling without replacement. So usually when we're doing an experiment, even if we haven't randomly sampled, or we're not sampling without replacement, right? But we're doing an experiment, we don't need to check the 10% condition. It is not necessary, right? If conditions are met, we use the 2-sample Z test for P1 minus P2. If we are testing the null hypothesis that there is no difference, right? Meaning that P1 and P2 are the same, P1 minus P2 equals 0. right? We use that 0 over here, and we use this Z statistic formula. Typically, this will be what we use. We will not really be looking at examples where our null hypothesis is that there is a difference, right? Or that there is some specific difference. If there was, then that value would go over here instead of 0. But we're not really considering those cases right now. So we get our Z statistic, and that is the difference between the population, the sample proportions, p hat 1 minus p hat 2 minus 0, divided by this standard error, but this is a modified standard error using the pooled sample proportion. Right, notice we're not using p hat 1 and p hat 2 over here. We're using this p hat c proportion, which is the count of successes in both samples divided by the sum of the sample sizes. And that is our pooled sample or combined sample proportion. We use that value for both of these fractions. Okay, so we have p hat c times 1 minus p hat c over n1 plus p hat c times 1 minus p hat c over n2. And we take the square root of that bad boy. All right, so this is specific to doing significance tests when we are assuming, right, our null hypothesis is that there is no difference between the two proportions. We use a pooled sample proportion. Right. In the cases that we're not really considering now in this class, that the null hypothesis is that there is a specific difference, you do not use the pooled sample proportion. Right, so if our null hypothesis is that p1 minus p2 is 0, we use pooled sample proportion, which is typically what we will use in this class. Right, and we have not necessarily seen an example of that so far in this class, unless you worked through some of the practice problems that are in Canvas. You may have seen one of these. So I wanted to run through the math of one of the examples, of an example problem, so that we can see that. Wait, before I do that, are there any questions? I know I'm running through this kind of fast. I apologize for that. Are there any questions? Is there anything I can clarify about comparing two proportions, sampling distributions, confidence intervals, or significance tests? All right, let's look at our example. All right, so on our example here, we have just before the presidential election in November 2008, a local newspaper conducted a poll of residents of a medium-sized city and found that 120 out of a simple random sample of 250 men intended to vote for Barack Obama, and 132 out of an SRS of 240 women intended to vote for Obama. Right. Is this convincing evidence that there was a gender difference in Obama's support in this city? Support your condition with a test of significance using alpha equaling 0.05. All right. So we have 120 out of a simple random sample of 250 men, 132 out of an SRS of 240 women. We're going to be using an alpha significance level of 0.05. We're doing a significance test. All right. Just for the sake of this example and for time, we will not be going through the whole 4-step process here. I just want to show you the math and using the pooled sample proportion. On an exam, like the AP exam, or when you do the free response questions and self-assessments in my class here, you're expected to show the full 4-step process. All right, so I want to just make that clear. So we have some values we need to kind of define here. Right, so I'm going to use p hat M for the proportion of men. So we have 120 out of 250. And that will equal 0.48. And we have the proportion of women for P hat W. And that's 132 out of 240, which is 0.55. Right? Since this is a significance test, right? And we're concerned about, was a gender difference, right? Was there a gender difference? Right? So it's our null hypothesis and alternative hypothesis will be as follows. Our null hypothesis will be that PW minus PM is equal to 0, meaning there's no difference. Right. And the alternative will be that there is a difference. PW minus PM is not equal to 0. So this becomes a two-sided test. Because we're not equal to 0. We could be greater than and we could be less than. This comes back later. Is there any questions so far? Any question about how I got my hypotheses?
How did you know if it was equal or not?
So the null hypothesis will always be equal to a value. The null hypothesis should never be an inequality as far as our class is concerned. So, and typically when we're doing the difference of proportions, we're just going to say the null hypothesis is that there is no difference, so it will be equal to 0. In our question here, right, is this convincing evidence that there was a gender difference? Right, that first part of our sentence there is telling us that we're going to be doing a two-sided test and that we're wanting to know, is there a difference either way? Was there, is it a positive difference or a negative difference? And a difference is a bit ambiguous. It could be that there's more women that support Barack Obama than men, or there's more men that support Barack Obama than women. So we're not concerned on which way that goes. If we were, that would change the alternative. But because we're just concerned, is there a difference between the two genders? We just say that it's not equal to 0. Does that explain it at all?
Yes.
Okay. Awesome. All right. So next, right, we have our hypotheses. We're going to be doing a two-sided test, which will come back later in our calculations. And again, we're using a significance level. Right, our significance level is alpha equals 0.05. That's a terrible 5. That's, 5. Yeah, that's better. All right. So these are the parts that we need to do our calculation, so to say, except for one thing, right? We need to use that pooled sample proportion. So we got to calculate that. And that will be P hat C is equal to 120 plus 132 divided by 250 plus 240. Right, so we have the total amount of people who support Barack Obama on the top, total number of successes, divided by the total number of sample between the two, 250 plus 240. Right. That equals 252 divided by 490, which is approximately 0.514. I did round that a little bit. So now this value here, right, this 0.514, that is what we will use to calculate Z, because in this case we're using the Z statistic for our test. All right, so now we're going to calculate Z, and we have Z equals some division. So we'll have P hat M minus P hat W, or actually I'm going to do P hat W minus P hat M. It has to be the same order as I set it up in the hypotheses, sorry. So we'll have 0.55 minus 0.48 minus 0, right, which is, for all intents and purposes, we're just doing 0.55 minus 0.48. Then we have our crazy big square root, which will be 0.514 times 0.486 all over 250 plus 0.514 times 0.486 over 240. Right, and again, that whole thing here is under that square root. Is there any questions about where I got all these numbers from?
Where did you get 0.486?
So the 0.486 is 1 minus 0.514. So remember, in our formulas here, right, we always use whatever the proportion is and then 1 minus that proportion. So these two numbers, the 0.514 and 0.486 in this example, should add up to 1. Right, essentially, the number in the parentheses is the complement to the first number. They add up to 100%.
Okay.
Awesome. All right. So we can put all this in the calculator just the way that this looks. I'm actually going to show you guys how to do that because this will be helpful to be able to get things to look the way you want them. So I didn't do this correctly. Hold on a second. Stop sharing my screen. And I'm going to share my screen. But just the screen. There we go. And then open my calculator. Can you guys see my calculator? Should be able to.
Yes.
Sweet. All right. So in the calculator, we're going to put this whole thing in here exactly the way that it looks here. All right. So using your TI-84, I can actually punch this in just the way that it looks here on my notes. So the first step to do this is I need to make a fraction. For our calculators to do that, you're going to hit alpha. Come on. Where's my mouse? There it is. Alpha. Y equals. And then hit enter. And it pops this little fraction up. Right, now I'm going to put the numerator of my fraction here for z into my calculator, which is going to be 0.55 minus 0.48. That's all that's essentially going to go into the numerator. So now I'm going to pop down to the denominator and I'm going to start my big square root. So I start by doing second x squared, which gives me the square root. Then I'm going to go back to alpha y equals, hit enter, and start my first fraction in the square root. So we get 0.514, parentheses, 0.486, close my parentheses, go down to the bottom of my fraction there to the denominator. I got 250 on the bottom. Click to the right to get out of the fraction, but I'm still under the square root. If you hit to the right again, it'll pop you out of the square root. We want to stay in the square root. Plus, do our next fraction, alpha y equals, enter, and we do the same, 0.514, parentheses, 0.486, close parentheses, click down, and we'll do 240. All right, now it's kind of bigger than our screen will show. Then I'm going to click out of everything. So now my cursor is all the way to the right. I can't enter anything into my fractions anymore. And we'll say, okay, let's do our calculation, hit enter. And we get the z value, right? 1.5498, la 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 la. Using table A, we can only use up to 2 decimal places. So we're going to round this to 2 decimal places, right, to 1.55. Is there any questions about how I punch this in the calculator? Okay. So we get approximately 1.55, right? When we look this up on table A, right, if I just look up 1.55, positive 1.55, it will give me the proportion under the curve less than that, which is going to be like a lot. It's a large proportion, but remember, I'm not concerned about that whole proportion. I want the 2 tails. So I'm looking for what's greater than 1.55 and what's less than negative 1.55. Right? So to get the proportion, quote unquote, faster, I'm going to look up negative 1.55 on table A and use the proportion that goes along with that, because I don't have to do any extra calculations for that proportion to be correct. Right? If I look up positive 1.55, I then need to subtract that value from 1, and then I have my proportion. One less step, just look up the negative value, and you get the proportion you need. Right? When we look this up on table A, right, we get a p-value equaling 0.0606. All right. This value here, we're not done. This is a 2-sided test. We multiply this by 2. All right. So we take this 0.0606, multiply it by 2. And we get 0.1212. That is the actual p-value. All right. Now we have enough information here to essentially make our conclusion. Right, this p-value is greater than alpha, right? So since our p-value of 1212 is greater than alpha 0.05, we failed to reject the null hypothesis. We do not have convincing evidence that there is, or that there was, a gender difference. I don't know if I spelled that right, sorry. Among men, women who supported Obama. Okay. Are there any questions?
No, but is this no going to be on the Canvas page?
Yes. Yes, I'll have it loaded for you guys. All right. So yeah, I wanted to just make sure and show you guys an example of this because it wasn't something we necessarily specifically saw yet. So I wanted to make sure that we covered it because you will see this type of thing. All right, so then section 10.2 is comparing two means. Right, we have our, again, sampling distribution, confidence intervals, and significance tests that we can do when comparing two means. Once again, with sampling distribution, we must check two conditions. Right, we have the normal large sample condition in this case, which in chapter 7 we called the central limit theorem, which allowed us to assess normality. And our 10% condition. The normal large sample condition is if our parent population was normal, our sampling distributions will be normal. It goes for both parent populations. Or if both sample sizes are sufficiently large, meaning greater than or equal to 30, right? If that happens, then again, we can assume that our sampling distribution will be normal. If neither of those two things are met, then we have to graph our data, look at the two histograms or dot plots, and make sure neither of them are strongly skewed, which means it is like a very obvious skew, and make sure that there are no obvious outliers. If there is no strong skewness and there are no outliers, we can then use or assume normality and use our t distributions and things like that, and do our sampling distribution calculations. So when conditions are met, we can calculate the mean. Right? The mean of the difference of the sample means will be equal to the difference of the population means, mu1 minus mu2. And the standard deviation of the difference of the sample means will be the square root, right? This big old square root of the population variance divided by n1 plus the population variance for population 2 divided by n2. Right? And so again, in this case, we should know the mean and standard deviation of our populations. Right? Otherwise, we can't really do these things. Once again, when we have these two values, the mean of the difference and the standard deviation of the difference, we can then use those along with table A. Right? And even though we're dealing with means, in this case, when we're doing sampling distributions and we get the mean and standard deviation this way, we use table A with means. We can standardize a value, determine proportions and probabilities using table A. Right. We then go on to confidence intervals. Once again, always check your conditions first. And again, just as in with proportions, when we're doing confidence intervals and significance tests, we're performing some form of inference. We must use the 4-step process. to do all of our steps. Right, so we check our conditions, random 10% normal large sample. Again, this 10% condition is only necessary when we are sampling without replacement. Right? When conditions are met, we use the 2 sample t interval for the difference between the means, mu1 minus mu2. We use this formula here. We have the difference between the 2 sample means, x bar 1 minus x bar 2, plus or minus our critical value t star. And just similar to how we find our critical value for proportions, t star depends on the confidence percentage that we're interested in. And we find that using table B along with the degrees of freedom. Along the bottom of table B, there's a bunch of percentages, confidence percentages. You find the one that you want, and then follow that column up until you intersect with the degree of freedom that we have on the left-hand column, and then that is the t star value. There will be only one degree of freedom used between the 2 sample sizes. Whichever sample size gives you the lower degree of freedom, that's the one you use. And then that gets multiplied by the standard error, right, which is the square root of the variance of sample 1 divided by n1 plus the variance of sample 2 divided by n2. And that will give us our interval. Then we have our significance test. Once again, check your conditions, random 10% normal large sample. When conditions are met, we use a 2 sample t-test for mu1 minus mu2. In this case, we are using a t statistic and t distributions. Once we have this t value, we use table B with the degree of freedom. Again, that is lower between the 2 sample sizes. And this applies to when testing the null hypothesis of mu1 minus mu2 equals 0, or if there is some hypothesized value. Whatever this number is, the mu1 minus mu2 equaling a value, which typically will be 0, but in some cases it might be a value, that value will go over here in your formula. Right? And t equals the difference of the sample means minus the difference of the population means, or the assumed population means from your hypothesis, right, divided by the standard error. Right? There is no special case or like a pooled sample or a combined sample thing like there is for proportions. Okay, there's just the standard error, just the same as we used it in confidence intervals. Okay. So, are there any questions or anything I can clarify about sampling distributions, confidence intervals, or significance tests for means, difference of means? All right. So then lastly, what I want to do is look at these examples on when you would use a matched pairs procedure or a 2 sample t procedure. The matched pairs goes along with using a 1 sample t procedure from the end of chapter 9, which we briefly talked about at the end of chapter 9 a couple weeks ago. And then 2 sample t procedures is what we've been using in this chapter with the difference of means. These 2 things deal with means, comparing means in some way. This doesn't necessarily apply to proportions. So what I want to highlight here is the 2nd and 4th example, which specifically deal with when we would use a matched pairs procedure, where we would just have a 1 sample t procedure that we would then use, what we did in chapter 9. So the first one here, or example 2, but the first one we're going to talk about, right, says to test the effect of background music on productivity, factory workers are observed. For 1 month, each subject works without music. For another month, the subject works while listening to music on an MP3 player. I just don't know why that's there. Works while listening. Okay, that makes more sense. The month in which each subject listens to music is determined by a coin toss. Right, so this is an experiment. We have random assignment. All right, so we'll have conditions met, so to say. However, this ends up being a matched pairs procedure, T procedure, in which case we would have one sample of means that we will then be using T procedures on. And this is because we have a single individual that is getting both treatments. And then for that one individual, the value we're interested in is the difference of productivity, whether they produced more or less of that, whatever they're producing. And then that single value of the difference is the value that we perform T procedures on. So we end up with one sample, one set, sample. Each individual gives us one value. All of those values are then used as our one sample procedure stuff. So we only get one set of values. Right? And so that becomes our matched pairs. Right? In the case when we have two sample procedures going on, we will have two sets of sample values that we will then compare. Right? Which then each sample produces a single mean, right, which we then use to do our procedures with. Okay, we end up with two means. In this scenario number 2, we end up with a single mean at the end of our experiment between all the workers, the mean difference. All right, and then we have scenario number 4, to compare the average weight gain of pigs fed 2 different rations. 9 pairs of pigs were used. The pigs in each pair were littermates. A coin toss was used to decide which pig in each pair got ration A and which got ration B. So again, we're interested in the difference in weight gain between the 2 pigs in each pairing, right? At the end of the experiment, we're only collecting one value from the 2 individuals, right? And so then that single value becomes a single sample between the 9 pigs, and we get a single mean difference in weight gain, right? If we conducted this differently and created if we used 18 pigs and randomly assigned them to 2 different groups, and then randomly assigned which of the 2 groups would get which ration, right? And then maybe compared their average weight or average weight gain between the 2 groups, that would be a 2 sample procedure, and we applied to what we did in chapter 10. The way they have this experiment set up, it becomes a 1 sample thing, and we have matched pairs. Is there anything I can clarify about this? Are there any questions? Alrighty. Stop sharing my screen. So that's kind of the wrap up that I wanted to do for chapter 10. And I wanted to highlight the 2 things that pooled sample proportion when dealing with a significance test for difference of proportions, and knowing when to use a matched pairs T procedure versus a 2 sample T procedure. Based on how our experiment or our sampling has been set up. Right? We need to be able to tell the difference between which one to use. Right? So that's all that I wanted to do today. I'll make sure that these notes get posted in the Canvas. If there are any other questions, comments, or concerns, please feel free to stick around and ask, or send me an email or message later asking for help. And again, tomorrow we'll be going over some AP exam prep things for making sure that we're getting ready for that. So I hope you all have a great rest of your day, and I will see you tomorrow.